Welcome to chapter 4, where we are going to talk about various other applications of derivatives. Now, this first lesson is talking about tangent lines. So let's review really quickly what a tangent line is. So anytime, let's say I have a graph here, and I have a cubic function. Anytime I pick a point on this function, I can draw a line that's going to touch that function exactly once and then be done. That's called a tangent line. It's also where the phrase go off on a tangent comes from. You start at a single point, the curve goes this way, the tangent goes that way. You're off on a tangent. But that's what a tangent line is. Quick reminder, the slope of this line is the very definition of what a derivative is. A derivative is the slope of all the tangent lines. That's what a derivative is. Now, this lesson is about using tangent lines. So let's review one last thing. This tangent line, this red line here, is linear. And it will always be linear. Tangent lines, whenever you draw them, will always be linear lines, which means I can write them using my point slope form, because that is a linear form. So then if I can write them in point slope form, all I need is a point and a slope, and then I can write an equation of my tangent line. Now let's get into what this lesson is actually talking about. This is called local linearization approximation. And basically what it's saying is there are some equations that are really hard to find values on. So, for example, if I know that this point is on this equation, but what I want to know is this point, 2.1 comma what? I really want to know what this point is on this equation. Well, if I plug 2.1 into this, I can solve it, but it gets really gross really fast. So this idea is using a tangent line to approximate what that point is. Now keep in mind, this is only an approximation. It's not exact. So it's saying, if this is my point, if that's 2 comma negative 2, and I want to approximate right there, 2.1 comma something, I want to know what that point is. Well, because those are so close, if I find that point on the tangent line, it's going to be pretty darn close to what the point is on the curve. That's what local linearization says. If I find it on the tangent line, it's a pretty good approximation for the actual point on the curve. So we're using a tangent line to approximate the point on a curve instead of going through all those solving steps, which tend to be kind of gross. So let's do an example right here. I have this point goes through this graph. I want to approximate this. So the first thing I'm going to need is to come up with the equation for my tangent line using the point given to me. So this is x1, this is y1, so I'm going to have y minus y1, which is going to be a negative 2, so plus 2, equals m x minus x1, which is 2. So now I need to find m. Remember, m is the slope of the tangent line, aka the derivative. So what I'm going to do is use this equation that I have right here to find my derivative and plug in my point. So this is going to be an implicit differentiation. So I've got 2x plus 2y dy dx, because that's the derivative of y, plus 2 dy dx, because that's the derivative of y, equals 0, because the derivative of 4 is 0. So let's start to solve for dy dx. Actually, let's start to shorten some things. You guys are getting fast at this. At this step, I'm going to take my dy dx out. So far so good. Divide by that stuff. So I have dy dx equals negative 2x over 2y plus 2. And now remember, I'm trying to find m. M is my derivative or my slope at my point. So I'm going to plug that point in and solve. So I've got negative 4 over negative 4 plus 2, which is negative 2, which is a positive 2. So I come back over here. My m is 2. And now this is the equation of my tangent line. Found my slope, found my point. So now I want to use this equation to approximate this point. I want to approximate 2.1. So I'm going to plug 2.1 in and simplify, solve this for y. Like so. So we get y equals negative 1.8. So that should be a pretty close approximation for what the y value would be at this x value. So with that, I want you to try when x coordinate is 1.9. So pause the video. You should be able to use the same tangent line equation. You're just approximating for a new value. So plugging it in, finding a new value. Pause the video, try that one out. Welcome back. You should have gotten negative 2.2. If not, you can go back, pause the video, look over my work, and figure out what happened. Now let's try number 2. We're using local linearization. So anytime you see those keywords, you should think equation of a tangent line. So I need my point and I need a slope. So if I look, there's my point. So there's x1, y1. So I've got y minus 3 equals mx minus 2. And it looks like right there is my m. That is the slope, the derivative, at my x value. Note that these x values are the same. That's how I know it's my slope at that point. So I'm going to have y minus 3 equals negative 2, x minus 2. There's my m. Now I want you guys to pause the video, use this equation to approximate f of 2.01. So plugging that in to approximate what the point would be. Welcome back. You should have gotten f of 2.01 is approximately 2.98. So that is our first application for derivatives for chapter 4. In the next video, we'll go through a graph and talk about one other application.